All right, hello, good morning. It is yet another lovely day of MENG 310 Fluid Mechanics. This is the third lecture in the series, and let us begin. So this lesson will cover sections 2.1 and then 2.3 to 2.31 and 2.5. We have a few lesson objectives this morning. First, I wish to apply Newton's second law to a static fluid element in order to obtain hydrostatic pressure equation. Second, I wish to apply the hydrostatic pressure equation to determine pressure on various points in a fluid at various depths in a container with several, or at various depths in a container with several fluids. So, if you remember from the previous lesson, one thing we did was define exactly what we mean by hydrostatic. And it kind of is revealed in simply the name. Hydro, meaning in this case any fluid, and static, meaning stationary, or at least not undergoing any acceleration. So an object, if you remember from engineering statics, an object can be in static equilibrium even if it is moving in some reference frame. It just cannot be experiencing any acceleration. Oh, I should say hydrostatic equation for pressure is what we're looking for. Hydrostatic equation for pressure. And that's what I want to try to derive today. The hydrostatic equation for pressure. So again, statics again, the hydrostatics is the study of forces applied to fluids at rest, and that is fluid statics. So let's look at the pressure at a particular point. Let's look at the pressure at a point. At a point. Pressure at a point. So let's say we have I'm going to draw a lovely, high quality 3D axis, which is going to end up very bad, but that's okay. So I'm going to draw an X, Y, and Z axis here. Let's see. Actually, I'm going to make it maybe more in black. Something like, maybe something like this. So let's say we have an X and a Y and a Z axis with maybe a Z like this, a Y like this, and an X axis like here. So I'm going to draw a little element. I'm going to draw a little element inside a fluid body. So let's say we have an X, a Y, and a Z axis. Now I'm going to project a little backwards from this. Let's say I project this backwards and I look at a little sort of triangular prism in this fluid. So I'll take this up here, like this here. Man, that looks really bad. And then this is going to connect here and here by hypotenuse. And this will be right angle here, and this will be right angle here. And like so here. Okay, so I'm going to label some dimensions now that I will reference as we go through. Well, this is going to be theta. It's sort of the angle of elevation. Delta x is going to be length along x, and actually let me label the x-axis so that's a little extra clear. I have my x-axis, I'm going to have my delta x. I'm going to have my delta y, the width of this element in the y direction, delta y, and then delta z, and then the hypotenuse I'm going to call L. Now let me look at this from the side. Let me look at this from the side here, or sort of an elevation view. If I look at this from the side, I'm going to have a few different things. So I'm still going to have my x and my y, or sorry, my z, I should say. And I'm going to consider this a body. Basically, the whole point of what I'm trying to do is I'm taking this element and then I'm going to look at what forces are acting on that body. So again, this is going to be theta. This will be delta x. And this will be delta z. Delta z, like shown. And L. All right, now let me show the forces that are acting on this body. So I'm going to have P1. These are going to be distributed forces, pressure forces. Say I'm going to call this one P1. Then I'll have another distributed force on the bottom here, P2. Basically, what I'm going to do is I'm just drawing all of these out, showing all the different forces on here, and then I will go to derive and combine them to a final pressure value. P2 here. And then along the top, I have another distributed force. All of these forces are, I'm looking at normal forces, because pressure will be exerting a normal force on surfaces, not any kind of tangential force. So I have 3 distributed forces, each one on one of the faces of the element. At least in terms of 2D. There would also be some force into the sides here, although kind of clearly that's going to cancel out. I'm not really going to worry much about the y direction, because I think it's fairly straightforward, that fairly self-evident, that the forces in the y direction on this are going to cancel out. So this is going to be P3. And now the P3 will combine together to an equivalent force here. So I have pressure 3, but I could also have an equivalent force, P3. And let's look at how this would work. So if I wanted to, basically I'm trying to do a little trick here. This isn't necessarily an equivalent force. I'm just showing how an equivalent force would be broken down in different axes. Well, it would have a y, that looks really bad, and a z term, obviously. And if I separate this out a bit, the vectors are going to work like this. I'm going to have P3 like this, which is the actual force, and then we'll have components, P3 cosine theta acting down, and P3 sine theta acting horizontally. And again, this is just showing how a force applied here is going to break down, and then I will work with this as I work through a further derivation. So again, this is a fluid prism that's sliced at a certain plane. And because a fluid, if you remember, can be sliced at any plane, because the reason it can be sliced at any plane is because there is no shear on it. We defined that earlier, that a fluid, by definition, will not be able to experience any kind of shear force, and so it will not have, she will have shear on no plane, or it will not have shear on any plane. So again, fluid prism, I have a fluid prism, slice at some angle theta, slice at angle theta, and it is static. It's going to be static, so there will be no shear on any plane. There will only be normal forces applied. Now, if you remember in the previous lesson, we looked at a case where fluids actually can have shear, and that is the case where the fluid is moving. We were looking at deriving definition, or the engineering definition of viscosity, and yes, in that particular case, you may have shear, but then the fluid is moving. As long as we confine ourselves to a static system, there will be no shear on any plane of a fluid prism. Okay, so I'm going to use this, and I'm just going to use Newton's second law and go through a few simple derivations and see what happens. Newton's second law, of course, being the sum of forces equal to mass times acceleration, which you remember from mechanics of materials and from engineering statics and from physics classes before that even. And so Newton's second law, all I'm going to do is add up the forces on each plane. And remember, each of these P's is a pressure. So in order to do a force, though, I need to multiply it by a certain area in order to produce a final value, and in order to produce a force value. So if I do a sum of forces in the x direction, well, this is going to be equal to 0 because it is static. This is going to be equal to P1 times delta z times delta y. delta z times delta y. If you look here, P1 is applied on the horizontal surface here, and so the dimensions of this rectangle are delta z times delta y. And then minus P3, oh, that's a beta, P3 times sine of theta times, so that's going to give me my the component of this pressure in the x direction, and then I need to multiply by the appropriate area, which is L delta y equals 0. However, something interesting is going to happen now. If I look at this, I can do something really neat here. L sine theta, if I look at my geometry, L sine theta is actually just equal to delta z. So suddenly I have P1 times delta z. Actually, let me just write it out here. Show a little more work here. So what I'd end up with is P1 times delta z delta y minus P3 delta z delta y equals 0. Oh, I see the same thing here and here, so I can cancel those out. And so I can conclude very quickly that P1 must be equal to P3. P1 must be equal to P3. If I do a sum of forces in the z direction, this is going to be P2 times delta x delta y. And in this little element of fluid that we're considering, it's important to take into account that this is small. In other words, this is a differential element. The size of the prism is small relative to the depth of the fluid, which is why we can consider which is why it's not surprising the pressure is coming out the same. Minus P3 times cosine theta times L delta y. Let me put something like that, and this equals 0. And I can do the same sort of thing when I realize that cosine theta times L, well, this here is equal to delta x. And from this, using the same sort of trick, I can then very simply conclude that P2 is equal to P3. Or if I were to combine all this together, I can say that P1 equals P2 equals P3 equals P. So, the pressure in a fluid at a point essentially will be omnidirectional, is what I'm really trying to get at. The pressure in a fluid at a point is omnidirectional. It doesn't matter at a particular point, at a particular depth, at a particular point, pressure is going to be acting equally in every direction. That is hydrostatic equilibrium. And really what this comes down to is Pascal's law. So a more formal definition of this, or a more formal expression of this, is Pascal's law. Not to be confused with Pascal's triangle or Pascal's wager, which are two different things entirely. Pressure is independent of direction. Pressure is independent of direction as long as no shear stresses are present. The moment that changes, then this assumption is no longer true. But as long as it is, we're not going to have a problem, as no shear stresses are present. And mainly this is true when the fluid is in static equilibrium, or when the fluid is stationary. So again, pressure is acting with equal intensity in all directions. Now, I want to move on to sort of the next application of this, or the next continuation of this, the next logical step, you might say, and that is pressure variation in a fluid at rest. So previously we saw that at a particular point, the pressure will be acting equally in all directions. But that was talking about one specific point, one specific location within a fluid, a small pressure prism. Now I want to look at throughout the fluid. I want to see how will things vary with depth primarily. And so let me draw another prism here. This time I'm going to draw a rectangular prism and use this to investigate how pressure varies with depth. So let's make another oh so lovely 3D diagram. And I'm going to have X, Y, and Z. X, Y, and Z. And then let's draw this out. And this is going to be more of a cube I'm aiming for. Just another oh so lovely 3D diagram. Can you tell I spent many years in art school? Wow, that's pretty bad even for me. Okay, mutated though it is, that will be our diagram. If you like a nice diagram, I'm sure you can find one in the book. Okay, so let me label dimensions again. This is going to be the same kind of delta x. This is going to be the same delta y. And then I'll have a delta z. Now I'm going to show show 6 different pressure forces on this, one on each of the faces, and I'm going to have P4 and P3 acting horizontally. Let's say P4 and P3 acting horizontally. Let's do P1 and P2 acting along the y-axis here. P2, P1, and then vertically I'm going to have going upwards P6 and downwards P5. And there's one other force I need to show on this prism, and that is the weight of the block itself, the weight of the fluid itself. So all of the 4 pressure forces, P4, P3, P1, P2, P5, P6, these are applying forces external to this cube of fluid. So again, this is some cube of fluid within, this is some element within the body of a fluid, and there are going to, if I look at a cube, there are going to be 6 pressure forces applied. And all of these 6 are applied to the outside of the cube, but the one that is within it, the one that arises within the body force is the weight of the fluid itself, which acts purely downward. Okay, and now I'm going to do the same kind of force equilibrium that I did before, and we'll see what happens then. Okay, so force equilibrium. Let's do another more Newton's second law. Equilibrium, or equilibrium, as some people may say, somewhere. Someone may be saying that somewhere, maybe. Static case. So let's do a sum of forces in the x direction. Sum of forces in the x direction is going to be P4 times delta y delta z. Again, all I'm doing is taking the pressures and multiplying by the area that they're applied to in that direction, times P3 times delta y delta z is equal to 0. And hey, what do you know? The yz's and the yz's cancel out, and I get that P3 is equal to P4. Not a big shock. And then, if I do a sum of forces in the y direction, I get that I'll get P2 times delta x delta z minus P1 times delta x delta z is equal to 0. And if these will cancel out again, the delta x's and the delta z's cancel out, and I get that P2 is equal to P1. Not a big shock. And then, if I do a sum of forces in the vertical direction, a sum of forces in the z direction, I will get P6 times delta x delta y minus P5 times delta x delta y. However, right now I have to include the weight of the fluid. Minus W equals 0. However, I also know that weight for a fluid, weight is going to be equal to rho g times v. I'm using the fancy bar v to signify volume. And then I can cancel out the, well, let's think about this. This is going to be a little more complicated. P6 times delta x delta y minus P5 delta x delta y minus rho gv. However, v, the volume, can be expressed as delta x delta y delta z, and then all of this still equals to 0. And so then I can cancel a few things out, namely the delta x delta y, and delta x delta y, and I will then get that P6 minus P5 equals rho g delta z. Or finally, I could get to a final derivation of delta P is equal to rho g delta z. The change in pressure in a fluid is going to be equal to the density times the acceleration due to gravity times the change in height. And this will be our governing equation for simple problems of fluid statics. So in other words, the takeaway from this is the partial of pressure with respect to x is going to be 0. The partial of pressure with respect to y is going to be 0. But the partial of pressure with respect to z is not equal to 0. So in other words, in a static fluid, pressure changes only with depth. You can move left and right or horizontally. You can move horizontally. By that I mean you can move left, right, forward, and back, and the pressure you measure will not change in that fluid. However, if you change your height, the pressure will change. And interestingly enough, this pressure varies only with depth. This pressure varies only with depth, not the volume of the fluid. So, for example, some example I love to give is consider something like Hoover Dam. So this is just gonna be a quick qualitative example. The basic idea of a dam is that you are going to use a large structure to hold back water for the purpose of flood control, for irrigation, and for hydroelectric power generation. And if you look at a dam cross, especially a tall dam, if you look at the cross section of it for a large concrete dam, its cross section actually looks something like this. It's thin at the top, but it gets increasingly thicker as you go down. And the reason is simply because of the increasing pressure as you go deeper. So I don't know the exact dimensions of Hoover Dam, but it's fairly tall, fairly hundreds of feet high. It's a very large structure. It's a mixture of gravity dam and also it's not a pure gravity dam, I believe. I think it's a mixture of gravity dam and also a sort of clenching against the walls of the canyon, that kind of thing. But anyway, here's the question. So this is actually like Lake Mead, I believe. And it is, hundreds of square miles. It's a massive body of water. It's just huge. There's communities that have been built along it. There's recreational facilities, lots of boating, and it is a big lake, a massive inland body of water. Now, here's a question. let's say somehow I was going to build a structure the same width as Hoover Dam, but instead of needing to hold back an entire lake, it only needed to hold back 1 foot of water. Let's say I contain it, not a lake, but just 1 foot of water. How much dam will you need? If I only want to hold back 1 foot of water, how much dam would I need? Well, the answer, surprisingly enough, if you don't know fluid mechanics, is the same dam. So to hold that 1 foot column of water, you would need 2 Hoover dams, 1 in each direction. And I cannot draw to save my life, so you get the idea. You would need 2 Hoover dams, just as strong, just as heavy, just as massive, 1 in each direction. Even if all you wanted to do was to hold a 1 foot wide column of fluid in place, simply because the only force that we've noticed that the pressure in a fluid only depends on the height of the fluid. So the force it's generating is only going to be dependent on the depth of the water column. It doesn't matter how long this thing is or how wide, the force on the dam will vary based on the width into the page here. But in terms of, it doesn't matter whether this strip of fluid here is 100 miles long or an inch wide, it's still going to generate the exact same amount of pressure. All right, so next move on, I want to talk about reference planes a bit. So generally we're going to define a reference plane as measured from the surface. So if I have a fluid, the bottom here, a fluid here, and a little element here, there will be a certain depth, z. And we're going to measure z as as being 0 at the surface and increasing as we go down. So we're using z as a depth measurement. Now, let me look at a quick equation or a graph and see what happens to pressure versus depth. Well, from our simple equation earlier, you can probably already predict what this would look like. If I put a p here and a z, what would this graph look like? Well, it would look something like this. It would be a linear equation, 0 at the surface, and increasing at a constant slope, a constant positive slope. So again, would have a positive slope with then dz, dp. Now, if we use this reference frame, so another way to think of this is based on this reference frame, something interesting happens. The partial of pressure with respect to z is simply going to be equal to gamma. So, the partial of pressure with respect to z is going to just be equal to gamma, the specific weight of the fluid. Now, interestingly enough, note, gamma does not have to be positive, or not positive, it always has to be positive, sorry, not have to be constant. You can have different layers with different gamma, with different specific weights, or you could even have a fluid that was fairly compressible, and you'd sort of have a gradually increasing gamma as you went deeper in depth. Although for our cases here, today, we're only going to be looking at different layers. Could have different layers with different gamma values, different specific weights. Okay, so let's move on here. And I will look at the hydrostatic pressure distribution equation. So I want to analyze how it changes between 2 points. The hydrostatic pressure distribution equation. So let's draw this out again. Something like this. I've ruined everything forever. Okay. Something like this, with another surface here, another fluid surface, and Z will be measured positive downward. And let's say we have 2 points, 1 and 2. Point 1 and point 2. And then from this, I'm going to have 2 different Z values, Z1 and Z2. Z1 and Z2. So, let's see. Well, we know a few things. We know the partial of pressure with respect to Z is going to be equal to gamma. Now, what happens if I separate the variables? So what happens if I separate the variables here, and I get, say, a dP, some sort of dirty calculus here, equals gamma delta Z. And then let me integrate each of these. So P1 to P2, and from Z1 to Z2. What will we get? If pressure is constant, let me label that. If, or not pressure, if gamma constant between Z1 and Z2, well, the integral will be fairly straightforward. I can pull the gamma out. So I'm going to pull the gamma out. I'll have the integral from P1 to P2 of dP equals gamma times the integral from Z1 to Z2 dZ. And all I did was I said the gamma is constant between here at Z1 and Z2, so therefore I can just pull it out as a constant. And so therefore, if I do the integral, I will find that P2 minus P1 is equal to gamma times Z2 minus Z1. Or if I put it into sort of a final form, I can get what I'm really after today, which is that P2 is equal to P1 plus gamma times Z2 minus Z1. And this is the hydrostatic pressure equation for constant specific weight between 2 points. Hydrostatic pressure equation with constant gamma from 1 to 2. Equation. All right, let's look at some notes on this. Let's look at some of the subtleties of this. Note, So let's look at I just want to look at a few provisos or subtleties or interesting characteristics of this. So again, as we've mentioned, pressure is the same at any xy at any xy at a given depth z. At a given depth z. Pressure varies linearly if gamma constant. Okay, so let's look at this. Let's compare two different kinds of, say, fish tanks or something like that. Two different kinds of tanks. Say I have one tank that's kind of L or boot-shaped, and one that is a simple rectangle. So I'm going to have two different tanks, and I'm going to look at how their pressures vary. And this isn't necessarily intuitive, as we saw with the Hoover Dam example. Let's say these are the same depth, and let's say these are both filled with water. So let's say we have gamma W for gamma water. Both of these are filled with water. And let's say both of these are H units high and H feet high. Feet high, meters high, miles high, of course, doesn't matter. Now, let's say we have something here. Well, let's look at a few points. Something like this. All of these points here at the bottom of the tanks, all points, all of these purple dots have same pressure. It doesn't matter that I'm going back underneath this kind of, the toe of the boot, for lack of a better word. It doesn't matter. I'm going deeper into the fluid, and that's what's kind of weird about it, because if you look at, say, the distance from the surface, this point is actually going to be, a lot farther from the surface than this point here is. Here you could just get to the surface, you could just go straight upward. But here you'd have to go around, first left and then up, or up and around. And it may not be that, it's not that intuitive that they all have the same pressure, but it turns out they actually do. And then if I had something like this, 2 points inside the column would also have the same pressure. So a point here and a point here, these also have same pressure. And if you have two different pressures here, let's see. Say you have, now interestingly enough though, so we know that the pressure is going to be different. However, if you have different objects at different depths, physical objects, not just looking at pressures at points, say like different plates and things like that, there they can experience different forces because they'll have different cross-sectional areas. If we're looking purely at pressures though, the pressures will be the same. Okay. And if I'm looking between two different points, say something like this, well, we know that P2 is going to be equal to P1 plus gamma H, or gamma Z or gamma H here. Now, if I express this in absolute pressure, though, absolute pressure, say I'm looking between, if I define this as 1 and 2, P1, P2, what is the P1? Well, the P1 on the top of the fluid is just going to be the atmospheric pressure. So that's going to be atmospheric. So if I do this in terms of absolute pressure, P2, the absolute pressure at the bottom of the tank, is going to be P atmospheric plus gamma H. If I do gauge pressure, I'll get that P2, well, atmospheric pressure, because basically in gauge pressure, we're measuring relative to atmospheric pressure. So the gauge pressure is simply going to be equal to gamma H. All right, so maybe have time for one quick example. But I think it's hopefully fairly straightforward from here. So let's say let me walk through one quick example today. And we'll use our old friends Guyven and Find. So given, say you have a sand pipe, or a standpipe, sorry. Standpipe 80 feet above ground. Filled with water. Or 80 feet high, filled with water. And in terms of plumbing or mechanical systems, a standpipe is a long vertical pipe. And I want to find the pressure at a hydrant connected to the stand. And I will draw this out in hydrant connected to stand. So let's show this. Basically what we have here is we have a fire hydrant down here. And I'm looking at the pressure at this point here. And then we have a long vertical column. This might be something like a water tower providing pressure to the municipal water system. And this thing is full of water all the way through. And so, and we know gamma water is 62.4 pounds per cubic foot. And we know the height of this is 80 feet. 80 feet, and this is, again, Z. So, since gamma constant between 1 and 2, well, I can just use my simple equations. We'll deal with more complex versions of this later in the week. P2 is going to be equal to P1 plus gamma times Z2 minus Z1. We're looking for gauge pressure, so P1 is just 0 for gauge pressure. If unstated, I would assume gauge pressure in your problems. P2 is going to be 0 plus 62.4 pounds per cubic foot times 80 feet minus 0 feet, or 4992 PSF. Or if I want to say PSI, I can say P2 if I just divide by 144, that's 12 squared. This is going to be equal to 34.7 pounds per square inch. And that is a simple explanation, or a simple application of the basic equations of fluid statics. All right, that will do it for today. I hope you all enjoyed the lesson, and I will see you on Wednesday. And as always, thank you.